Section 5.5 discusses the second fundamental theorem of calculus, or as your book will call it, the fundamental theorem of calculus, the second part. And really what it's based on is thinking of the area under the curve, the integral function, as an area function. So notice where I start off here. I say the area function, meaning it's going to be a function in terms of x, starting at the x value of a is given by the area with respect to x is the integral from some number a to x of f of t dt. Now, notice it's saying it's an area function in terms of x, but inside the integral, it's in terms of t. Well, the reason you have to have it in terms of t there is because I'm using x as the limit of integration. You don't want the same variable on the inside as you have that you're evaluating it. So that t is really a dummy variable because I know that whenever I evaluate it, it's going to be in terms of the antiderivative f evaluated at x and then it evaluated at the constant a. So it will be a function of x eventually, even though the original function's in terms of t. So I need you to remember the variable on the inside of the integral, really irrelevant. But it cannot be the same thing as your variable that's in the limits of integration. Now, in this case, if we wanted to find the area from a to some value of x, then you would say, well, then the area accumulated by the time you get to a is 0. And that should make sense to you because you're asking how much area do you have between a and a? You don't have any distance to gain an area. So you can say, well, of course it's 0. Now, if I ask you, for example, to piggyback off of that, if I ask, for example, how much area is the function a of 3 if a of x is represented by the integral from 3 to x of f of t dt? Should be extremely easy. You know, answer 0. Why is the answer 0? Well, because if this is your area function starting at 3, then the area accumulated by the time you get to 3 would just be the area between 3 and 3, which means that you're going to take the antiderivative of small f, which would get capital F. You'd say, well, it's whatever this antiderivative is, evaluated at the upper limit 3, minus the antiderivative evaluated at the bottom limit, which is also 3, clearly 0. All that's saying is that you haven't given it any amount of x values to accumulate area if you're wanting to know how much area is accumulated by the time you get to 3, assuming you start at 3. Now, fundamental theorem of calculus part 2 is just saying that the derivative of the area function is just the function on the inside of the integral evaluated at x. So what it's saying is that if a of x is the integral from a to x of f of t dt, then the derivative of that area function, a prime of x, it's just the function on the inside evaluated at x, not at t. Now, another way to represent that, I could say, well, then the derivative of a to x of f of t dt is just the function on the inside evaluated at x rather than at t, because your limits of integration are going to be in terms of x. Now, in order to see why, because a lot of students look at that and say, I don't know what it's really saying. Well, think about that. If I have the area function a of x, and again, I'm saying it's the integral from a to x of f of t dt, I know that when I integrate this, I'll get whatever the integral is evaluated at the upper limit. Well, that's at x, minus whatever the integral of f is, capital F, evaluated at the bottom limit, which is a. Now, if we want the derivative of that area function, you would have to then go in and say, well, this is a of x, so a prime of x would be the derivative of the first function minus the derivative of the second function. But remember, a is just some constant. We know that the derivative of any constant is 0, but the derivative of capital F would just be small f. And you say, oh, well, then a prime of x, yeah, it's just equal to f of x. It's whatever your function is on the inside of that, no longer evaluated at the dummy variable. It's evaluated at the variable of interest x, because that's our limit of integration. And you can say, well, the derivative of a prime of x is just the function on the inside evaluated at x. Let's see a specific example of that. So if I'm asking you to find a prime of x, if a of x is the integral from 5 to x of t squared minus 5. Now, I already know my answer. What is a prime of x? If I could cover up the rest of the problem, I am already 100% certain that my answer is x squared minus 5. I can see that by just looking at it. You should be able to see that by just looking at it. You say, okay, all he's done is he's looked at the function on the inside of the integral. He's going to replace it with terms of x, so the answer is going to be x squared minus 5. To make sure you see how that works within the relation of if you work the problem out, you would go ahead and integrate this problem with respect to t. So you get t cubed over 3 minus 5t. Then you would evaluate that integral at the limits of integration from 5 to x. So we say, okay, let's plug in the top limit. That gives you 1/3 x cubed minus 5x. Then we subtract from that the lower limit of integration, which is going to be 1/3 times 5 cubed, 125 over 3, minus 5 times 5, 25. Now, that's the area function a of x. If I want the derivative of that, I just say, well, I need to go back and take the derivative of this answer. Derivative of these constants becomes 0. So that lower limit of integration all cancels out when you take the derivative because it's just a constant. So then I only have to worry about taking the derivative of the first two terms, and I see that that's going to give me x to the second minus 5, which is the same thing if I would have just looked inside the original and just said, just change the t for x and get x squared minus 5, because that's what it's going to end up being. That's what this second part of the fundamental theorem of calculus tells us. Now, let's look at another problem here. If I give you h of u, who is equal to the integral from 2 to u of the square root of t to the 4th minus t dt. Now, this time, I'm not capable of going through and using my techniques of integration to actually physically integrate it and then differentiate it. I don't know how to integrate this, at least yet, so that's not the way we do this problem. If I'm wanting you to find h of 2 and h prime of 2, first thing you'd say, well, h of 2, that's literally when you're going to plug a 2 in for u, and you say, well, h of 2, then I plug a 2 in for u. You already know that h of 2 has to be 0, because you'd say you don't accumulate any area by the time you get to 2, since your region is starting at 2. You just say, well, the integral from 2 to 2 of this curve, it's 0. Now, h prime of 2, you'd have to know what h prime of u is first. And you say, well, h prime of u is just my function on the inside with a u in the place of t. So h prime of u is going to be the square root of u to the 4th minus u. So h prime of 2 is going to be the square root of 2 to the 4th minus 2, or 16 minus 4. It's going to be the square root of 14. Now, if I look at another one here, and this one we could do out by hand, so I will. If I say, I want you to find f of x, or capital F of x, if lowercase f of x is equal to 1/2 x to the 5th. So I need to find the integral in this case. And I know that f of 5 is 0. Well, that just means that your region starts at 5. If you haven't accumulated any area by the time you got to 5, that means 5 is the starting point at which your area begins to accumulate. So I can say, well, okay, f of x is equal to the integral from 5 to x of the function f of x. Now, I need to put a different variable on the inside because x is my limit of integration that it will eventually be in the terms of. Typically, we choose t as the dummy variable on the inside. So I'll just say, well, this function on the inside is going to be 1/2 t to the 5th with respect to t. My power rule says that this is going to go to 1/2 t to the 6th over 6, which gives me 1/12 t to the 6th. Now I need to integrate that from 5 to x. And then notice what happens when you do that. When you integrate that from 5 to x, the x now takes the place of the t, and you'd get your 1/12 x to the 6th, or x to the 6th over 12. And then the fact that f of 5 was 0 tells me that my lower limit has to be 5. I plug a 5 into that function. I think 5 to the 6th power is that, goodness, 15,625, but we don't worry about that. I'll just leave it as 5 to the 6th there. And then we'd say all over 12. This would be your final answer for the function that satisfies the criteria there. That is the antiderivative of this function such that when you evaluate it at 5, you're going to get a 0. And clearly you're going to get a 0 if you evaluate it at 5. You can just look at it and say, yep, if I plug a 5 in for x, I'm going to get a 0. For my next one, some of the problems in this section, you kind of wonder why they're in this section. Most of them will be like the ones we've talked about. Others, this one really goes back to the previous section where you're just using the fundamental theorem of calculus part 1, the evaluation theorem. It's having you to integrate the cosine of u from pi over 4 to x. And so you'd say, well, the integral of the cosine is the sine, since derivative of sine is cosine. Now I need to evaluate that from pi over 4 to x. Well, the sine of the upper limit is going to be sine of x, and then evaluate the lower limit minus the lower limit minus the sine of pi over 4. We know that this is just going to be the sine of x and then the sine of pi over 4 minus the square root of 2 over 2. Pretty good problem. Now, another one similar to that. What if I ask you to integrate from 2 up to the root of x of dt over t? We know that this is the integral of 1 over t with respect to t, which has the integral of the natural log of the absolute value of t. Now, we need to evaluate that from 2 up to the root of x. I've already taken the integral, so now it's just a matter of plugging these in. I'll get the natural log of the square root of x, and since the square root of x is automatically positive or 0 anyway, I don't need the absolute value anymore. And then minus the natural log of the lower limit, and again, I don't need the absolute value, minus the natural log of 2. You could leave your answer like this. I preferred to go ahead and say that x is understood to be to the 1/2 power. I'll bring that 1/2 out in front, but you wouldn't have to do that. You could leave it this way or this way. Either way would be fine. For the next one, if I ask you to find a function or define a function f of x in integral form, if I'm saying lowercase f of x is equal to e to the negative x squared, and I'm telling you that f of 4 is equal to 0, automatically the fact that I'm telling you f of 4 is equal to 0 means you're going to start your integration at x equals 4, and you're going to go up to x. So please notice, I say, well, then f of x is equal to the integral starting at 4. Again, how do you know you start at 4? Because at 4, your area is 0, so you only start to accumulate area after x equals 4. So I'll say from 4 up to the value of x, and then in order to get this function in there, this inside, I have to use the dummy variable to represent that. I'll say e to the negative t squared dt. Now, when I integrate it, it'll be in terms of x, and it will give me the capital F of x. Gorgeous problem. One more like that. If I say I want you to take the derivative with respect to x on the integral from 1 to x of the sine of, again, the dummy variable t squared with respect to t. So you say, I don't know how to integrate the sine of t squared. I know how to integrate the sine of t, but not the sine of t squared. So I don't have to worry about integrating it because I can say, well, the derivative of this integral, whatever the integration does, the derivative will undo. So it's just going to be the function on the inside evaluated at the limits of integration. So instead of the sine of t squared, I get the sine of x squared. Why don't I have to worry about the lower limit of integration? Because it's a constant. And I know that when I take the derivative of any constant is going to be 0. So whatever the lower limit would have given me here cancels out and forms a 0, and I just have this function evaluated at the upper limit sine of x squared. Now that one was pretty straightforward. What if we're giving a function like this, and I'm supposed to say, I want to find the area function that represents this picture drawn. So this is kind of a strange scenario. And you say, well, if you just draw a picture and you're wanting the area function to represent it. First thing I did is I said, I'm going to, in this picture, it was already called y equals f of x. I'm going to go ahead and create a piecewise function to define the graph of this picture. In the beginning, I can see, well, as x increases, y increases with a slope of 1, and that's from 0 to 3. So it's just f of x or y is equal to x for the values of x between 0 and 3. But after I get to 3, it's just a constant function. So that's just going to be y equals 3 forever and ever and ever after that. So you'll see f of x is equal to 3, where x is greater than 3. Now, I know that the antiderivative of this function, because whenever I take the integral or find the antiderivative, it should represent area under the curve. So I'll say the antiderivative of this function should represent the area function. And that area function is going to start accumulating area at 0. So I know I start the integral at 0. And now I'll say, well, it's going to go the integral from 0 to x, where x is any number in here. And then it's going to start off where I have to use a dummy variable in there to represent the x. So I use a t. So f of x is going to equal the integral from 0 to x of t dt. And that's going to give me 1/2 x squared, sorry, 1/2 t squared to begin with. And I would evaluate that from 0 to x. You said, well, clearly that's just going to give you 1/2 x squared. So what I know is that, yes, the first part of this function is going to have an antiderivative of 1/2 x squared. And you'll notice I went ahead and put that down here. Now, this also has to represent the area of this function from 0 to 3. So that's what I put right here. I said, we know that the area A of 3 is supposed to be 1/2 base times height, 1/2 3 times 3. And you can say, well, the area is supposed to be 9/2 that's accumulated by the time you get to 3. So now I can say, is that going to be satisfied by this formula, A of 3? Yeah, 1/2 3 squared would be the exact same thing as 1/2 base times height. So when I came down to find the piecewise function that is the area function here, for my first one, yes, the integral of x is just 1/2 x squared. I didn't have to worry about any constant of integration. So I just said it's 1/2 x squared from 0 to 3. That's going to exactly find the area for any value of x between 0 and 3. But now after 3. So I said when x is greater than 3, the antiderivative of this function is just going to be the antiderivative of 3 with respect to x. You say, well, that's going to be 3x plus the constant of integration. And so now I know I still need f of 3 to equal 9/2. But if I plugged f of 3 over into this function, you get 3 times 3, which is 9. So I have to say, well, 9 plus c has to equal 9/2. Then that allows me to see that I do need a constant of integration for the second one to be negative 9/2. And again, that's just to guarantee that it's correctly measuring the area under the curve up to any point. F of 3 had to be 9/2. If I just plugged f of 3 into this function, I would get a 9. So I had to subtract 9/2 into this second portion of the piecewise area function. And then I can say after that, it's going to correctly estimate exactly, not estimate, it's going to exactly give me the area up to any value of x. Like if I plug an x value of x of 6 in, it'll tell me that the area is 18 minus 9/2, which you could say, well, that's going to be 36/2 minus 9/2, 27/2. I know the area out to x equals 6 has to be 27/2 units. And you could check it and add the area of the triangle plus the area of the rectangle that you would get. It's going to check out every single time. Now, those can be a little challenging to set up just because of having to solve for the constant of integration in each of these. The problems I'm more interested in this section are the ones like these last three here. These are gorgeous. So when I'm looking at these with you here, this first one, well, first of all, let me say, what's happening in these problems is a result of the Calc 1 derivative chain rule. What you're supposed to remember with the chain rule, if you have a function that you're trying to take the derivative of, and you know that it's a composition of functions, so if capital G of x is a of lowercase g of x, then the derivative g prime of x is the derivative of the outside evaluated at the inside times the derivative of the inside. So now, whenever I'm asking you to take the derivative of the integral of a function, don't make these problems harder than they are. First of all, I know, yes, the derivative and the integral are inverse functions. They're going to cancel out each other. But whatever the integral of this is, and we don't know how to integrate that, whatever the integral of this is, when I take the derivative, it's going to go back to become a sine function. But before I take the derivative, I'm plugging in my limits of integration. So that's creating an inside function. So notice, I'm saying the derivative with respect to x of the integral of this function is going to be that function evaluated at the limits of integration. So I get the sine of not t squared, but the sine of 1/2, or sorry, not 1/2, the sine of 1 over x quantity squared. So the 1 over x took the place of t in my function. But now, while the derivative and the integral cancel each other out, that limit of integration becomes my inside function. And that was not inside the integration. So now when I take the derivative, I have to multiply by the derivative of the limit of integration. So I say times the derivative with respect to x of whatever I plugged in, the 1 over x. And that's a result of the chain rule. Now, why don't I worry about the lower limit? Well, because it's going to be evaluating a constant. The integral of the sine of t squared evaluated at 1 would be a constant. The derivative of any constant, 0. So I only have to worry about the non-constant limits. And in this case, I'll get the sine of 1 over x squared times the derivative of 1 over x. I know that the derivative of 1 over x, I can think of that as like x to the negative 1 power. So its derivative is negative 1 over x squared. And you'll see I just put the negative out in front of the sine function and the x squared in the denominator. Fantastic final answer there. Now, for this next one, I'm asking you to take the derivative with respect to x of the integral from x cubed to 0 of sine squared t. So again, I don't even worry about the top limit of integration. Why? It's a constant. Derivative of any constant is 0. So I'll just say you could think of a 0 there. Now, minus the lower limit of integration. What's it going to be? Sine squared of the angle x cubed now, and then times the derivative of that angle, 3x squared. So my final answer for this problem, you just say, well, it's going to be the function on the inside evaluated at the limits of integration. It's going to be subtracted because it was a lower limit of integration, and then you multiply by the derivative of whatever you're plugging in due to the chain rule. And then I can say, well, my final answer is just negative 3x squared sine squared of x cubed. For my next one, I'm asking you to take the derivative from x squared to x to the 4th of the square root of t. You say, okay, so both, I'll have an answer for both my upper and lower limit of integration this time because I have variables in terms of x for both of them, and I'm taking the derivative with respect to x. So I'll say, okay, this upper one, you're going to replace what's inside the function, the t inside the function, with your limit of integration. You'll have the square root of x to the 4th times the derivative of what you're plugging in. And I can say, well, the derivative of x to the 4th is 4x cubed. Minus, and why is it minus? Because you always subtract the lower limit of integration, minus the function evaluated at the lower limit minus the square root of x squared times the derivative of what I'm plugging in. Derivative of x squared is 2x. Now, when I simplified this, I just said this first term is going to be 4x cubed times x squared for 4x to the fifth. The second one's going to be x times 2x for 2x squared. So I get 4x to the fifth minus 2x squared. This last one here. So this time, in order to get an answer, my function's going to need to be in terms of u. Well, my limits of integration are in terms of u. The original problem inside the integral, now the dummy variable is in terms of x. That's completely irrelevant because whatever the variable is going to be replaced with your limits of integration. So I'll say the derivative of this integral with these limits of integration, negative u and 3u plus 9, is going to be the function on the inside. In the place of the variable x, you're going to put it with the limits of integration. I'll have 3u plus 9 quantity squared plus 1 under the square root. And then where did this 3 come from? Because you always have to multiply by the derivative of the limit of integration. So times 3. Now minus the lower limit. Well, the lower limit's going to be the function. You're going to replace the variable in there with your lower limit. The negative u is being squared plus 1 times the derivative of negative u with respect to u, which is negative 1. So now all I did to simplify this, I brought the 3 out in front of this first square root. I said 3u plus 9 quantity squared is going to be 9u squared plus 27u plus 27u for plus 54u. And then it would be plus 81 plus 1 for plus 82. So I get 3 on that square root. And then my second one, instead of being subtracted, it's added because it's minus a factor of a negative 1 plus the square root of u squared plus 1. Gorgeous problems. Now, this fundamental theorem of calculus part 2, once you start getting comfortable with it, you'll think most of these problems are pretty easy, but it can be a little challenging to get used to. So just be patient with yourself as you're learning these new tricks, and once you learn them, it'll make these problems so easy. So now please do try the Achieve assignment for 5.5. Let me know if you have any questions.